Okay. Hello, everyone. Today we have the pleasure of continuing the course titled Density Functionals for the Kinetic Energy Theory and Practice, presented by Dr. Paul Ayers from McMaster University in Ontario, Canada. Welcome, Dr. Ayers. Please go ahead with the course. Thank you.
Okay. So we talked some about kinetic energy functionals, and then last time we talked a little bit about one matrix functionals. And I'm going to sort of continue along those lines. One thing we talked about a good bit last time was irrepresentability, right? So we talked about how to know whether a density matrix was irrepresentable, right? So as a sort of both a refresher on that, and as something that maybe is looping back to tying things together, let's go back and now we're going to talk about whether a density functional is irrepresentable, okay? So we're going to say, what does it take for a kinetic energy functional to be irrepresentable, okay? So let's think about a kinetic energy functional. Kinetic energy functional. Okay, so this would be our kinetic energy functional. And what does this mean? Like if we say that a given density goes to a given value of Ts, what does this mean in practice? What it means in practice is that I give you a density, it goes to a wave function, or more generally, a density matrix, and then this gives you Ts, right? So what does that mean? That means there's some wave function or density matrix that gives you both the density and the Ts, right? So this is the nature of irrepresentability for density functions specific to kinetic energy. We're going to generalize it a little bit because it's kind of fun. But let's start with this because this is going to be the simplest one we can imagine. Okay, so okay. Really, this is just, I should even just be clear. This is really just, at this stage, just kinetic energy functional in general, because I haven't said anything about being non-interacting, right? So, okay. So this is to say, if this isn't true, then you give me a density, you give me a value of Ts that doesn't satisfy this, that means that this is ridiculous. There is no system that has that, right? So let me give you explicit example. If kinetic energy is less than this number, right? Which is the bicycle kinetic energy. We know the bicycle kinetic energy is a lower bound. So if it's lower than the lower bound, then this is not a legitimate kinetic energy, right? Trivial example, right? So we're going to play the same game we played last time, right? Well, I'll leave it up. I don't really need the space probably. So in the same way as before, the set of irrepresentable TS, right? These are the irrepresentable, if you like. So this is the set of values of T and rho that are irrepresentable. It's going to be a convex set, right? And if I have an element outside the convex set, right, then there's some way of dividing my element from it. Now, within the convex set, I know what's happening, right? So now I can think about this. This is a one electron thing. Now I'm going to think about TS specifically. I'm going to go back to the one electron case. The boundary of this set, so within this set, I can think about the fact that within this set, I always end up with an energy that's higher than the true ground state energy. Okay, so within the set, if I do a minimization over TS and rho that are irrepresentable, then this will always be greater than the ground state. And the specific type of form I'm going to choose is a non-interacting form. So my energy expression is going to be equal to the Kohn-Sham kinetic energy plus the integral of the density times. And I'm going to need, in fact, an extra factor K here, which is the mass. So the K is the mass, if you will. Okay? It's 1 over the mass, right? And all I'm doing here is I'm just saying, here I have a density. What goes with density? Potential. What goes with a number, another number. And so a hyperplane here is defined exactly by, well, provided that it's touching the point. It's defined exactly by, this is the ground state of this expression for some V and some K. Okay? Some mass. It doesn't really matter the K because I could always move it over to the V if you don't like thinking about changing the mass, but that's what you're doing. You're changing the mass. What? Oh, it can be, of course. Right there. It's equal. Yeah. So this one here, I know that it's too low for at least something, right? So what does this tell me? It tells me that this is by definition lower than this. So this is the E ground state associated with K and some VS. So, and again, let me just write it. I'll write it in the corner here just so it's in. K equals mass the minus 1. You like, right? So this element here has the property that TS or really to say is less than the ground state associated with K and VS. For some K and VS. Now I can clean this up a little bit, right? And so what does this mean? This means that TS is less than okay. And the only cool thing about this is that at this stage, I can say that TS is less than or equal to, this is the true TS. So TS, you say of VS. The K's cancel each other out because I have a K here and I multiply by 1/K. So I just get the normal kinetic energy. So this is the kinetic energy that goes with this external potential. Plus integral which is just to say that there is some system for which the true kinetic energy is bigger than this one, right? Just all it says, right? So this is obvious. It's the same thing that we had before. It said you go below the true ground state, right? Now I'm going to play this with a little bit more interesting game here. A game that I think people are less used to seeing. So I'm going to do something different from this. I'm going to try the same thing, but I'm going to say, instead of doing TS, I'm going to do the local kinetic energy. Okay. Now, in the paper I wrote with Shubin Liu, we dealt with the fact that there's lots of ambiguity in the local kinetic energy. I'm going to choose just one, because whatever your local kinetic energy is, you have to choose how you want to define it. And it's going to be much easier for me if I define the local kinetic energy as Ts of R equals sum over I of even though this isn't the kinetic energy I don't, right? It's not positive definite, so it's a little bit inconvenient, but it's nicer when you think about the Schrodinger equation to think about this local kinetic energy. Okay. And I can play the same game now. So I have Ts of R and rho of R, and there has to be some system that gives me those two numbers at the same time, right? It's not at all obvious that there's a system that has this Ts and also at the same time this density, right? So not every pair of Ts and rho comes from some system, right? I'm going to choose only the ones that come from some system. Again, it's going to be some convex set, right? Again, I'm going to have some boundary. And again, if I'm not inside the convex set, so I have a bad Ts and rho, what does that mean? That means that the integral of something I'm going to call is less than whatever the ground state for this system is. And what's the ground state for this system? The ground state of this is the minimum over, well, this is going to be we can choose Slater determinants because it's going to be a non-interacting system. And it's the minimum of this system. Okay. So this is the ground state of a system. Now we have to think about what this means. And this becomes easier if I just write this as this is the minimum over phi of some system. I'm going to rewrite this in a way that I think is more intuitive. Okay. So the nice thing about this is this you can think of as a local effectiveness, right? Which is weird, but not weird to physicists to think about local effectiveness, right? So this is a constraint now for TS and rho. Okay, now this is going to be interesting, and I'm going to sort of take a step back. But I want you to remember this sort of key result. This means, in fact, that I can define using the same as the normal tricks. I can define how should I write this to be clean? Well, let's not worry about it for right now. We'll come back to it in a second. Okay, so this is a little bit of a complicated case. I want to think about a simpler case, right? But I just want to think about the fact here that if I write the exact functional, okay? So the exact energy functional. The exact energy functional. So E of rho with some external potential is equal to the integral of Ts of R plus okay. This should make sense to people, right? This is just me rewriting the exact energy as kinetic energy plus interaction with the external potential plus Coulomb plus some sort of exchange, right? Now, I'm going to be allowed now to write is going to be the supremum over zeta and V of the energy with zeta and V. Should do this. Minus integral okay, and I'm just going to put in, I should have put it in earlier. I'll put in a zeta here. It's obviously fine, right? I just generalized my Hamiltonian to include an extra term, right? It's okay. I added an extra variable for convenience, right? What I'm going to show in a little bit is that this functional is convex, right? And because this functional is convex, we're going to get an interest constraint out of this, okay? So I'm not going to show you for this because this is more complicated. It has two variables. I'm going to show you for the one variable case, but the proof is the same. Okay? So let me explain to I'm going to well, TS. Okay? So why is this interesting? Well, this gives you a constraint. For instance, it tells you that the second derivative of J of rho plus EXC of rho. And it tells you that the second derivative of EXC with respect to the kinetic energy is also greater, right? So these are useful constraints when you're trying to build density functionals, for example, right? So this is getting back into the kinetic energy side. This type of form is what you use in a meta-GGA, right? And this is a constraint on meta-GGAs, right? That the second derivative with respect to kinetic energy density had better be always positive. Okay. Now I'm going to do the proof in a very simple way. I'm going to do it just for the density case because it's easier and honestly, it's probably more fundamental. Right? So generalized constant, this would not be easy to do, right? Because I have to depend on a density, right? That said, this constraint is violated by essentially everything. And the reason is that the J is non-local. So this is saying, yeah, so this is the kernel plus okay. Now this is nice and positive. This, it's usually like a negative delta function, right? If you're doing a GGA, there's a negative delta function in here. And in fact, if you look at it, this is one of the arguments for why the exchange correlation energy functional has to be non-local. Is it has to know something about this is non-local, this also has to be non-local in general in order to satisfy this constraint. Right? So this is one way of thinking about that, right? So that's why this is essentially never true. Well, while we're at it, go to the very end of this. The presentation. We'll come back to this in a second. Yeah. Just keep going. Yeah. Yeah. It's going to be at the very end. You're going to see if, oops, didn't it show up? Cool. Can you go to like page 29? Okay, yeah. So here are the actual, so you can actually look at this here. This is Rev TPSS, and this is, I think this is one of the generalized gradient, the what do they call it? The meta GGA made simple, right? And you just look at this and you quickly see, well, the curvature, turns out the curvature here should be negative because this is the enhancement factor. It gets multiplied by a negative number. And it's okay, and then it's not okay, right? If you go to the next one, here is now the meta GGA made very simple, right? Again, it's okay, it's not okay. And then next. Yeah, here's the, in this case, you can't see it. This is actually the second derivative. This is scan and revise scan. And, you know, it's, well, number one, scan is a mess, right? Revise scan is okay, and then it's not okay, right? So basically, all the meta GGAs violate this constraint too. So despite everything John Perdue says about accepting the constraints, this one, at least this, the revise scan is not terrible, right? I mean, is it satisfied? No, but the other ones were terrible. This is like semi-terrible, right? So, okay, so this is the point of that. Now, can you go back to where I was writing? This one, a blank slide. This is fine. This is fine. Okay, so that's what I was going to show you. No, not published. I have a, yeah. I publish slowly, right? Right, so. But no, I mean, these are violated constraints, right? So I'm going to explain to you why this is convex. I'm going to do it with one variable, and I'm going to do it with f of rho, okay? So I'm going to show you that f of rho is convex, okay? So I'm going to write down the same functional I did, but now it's only going to have f of rho. And there's a generic trick, right? The generic trick is that f of rho is equal to, well, and this is true for any sort of functional, you're going to take the variable that goes with rho, which in this case is v. You're going to take a maximum. You're going to take the energy associated with that variable and for a given number of electrons, right? And then you're going to subtract off the linear part, okay? So that's the generic way that this works, okay? Now, this isn't as useful as I would like it to be, mainly because I buried a lot of complexity inside this term, right? So I need to think about what this term looks like. So this term, this is supremum over V of minimum over, we can say wave functions. It could be wave functions or ensembles. It doesn't matter. And this is going to be T plus VE plus some I equals 1 to N. Okay, so that's the functional. I just wrote it down more explicitly. Now, you remember we talked about convex before. Convex means that I need to think about something that looks like T rho 1 of R plus 1 minus T rho 2 of R. Okay? So I'm going to write down this expression, right? So okay, so I don't know exactly what's going on yet here, but one thing I know is that I can rewrite this as the supremum over V. I don't know what V I'm going to get yet, but it's a minimum over psi of psi T plus. I'm sorry, I should have said this is R, but I'm running out of space. So I think it's clear what I mean here, right? Now, in general, I don't know exactly how to deal with this, but I'm going to play a game, okay? And the game I'm going to play is I'm going to break this into two pieces because I know that on the other side, I need something that looks like T f of rho 1 plus 1 minus T f of rho 2, right? So I know I need two pieces. So I'm going to break this into two pieces. I'm going to do supremum over V, minimum over psi. And I'm going to write this as psi. Well, let me write. I'll break it in two steps. Well, Okay. I'm getting sloppier and sloppier with my notation here, but this just means integrate rho 2 times v, right? But I'm running out of space. Okay, I've broken this. This is a linear operator, right? So I have every right to break this into two pieces now. I can write this as the supremum over v, so minimum over psi of t and let me just go on and subtract minus t. This is rho 1 v minus 1 minus t rho 2 v. Okay. Okay, so now I'm going to we need to start thinking about what I'm going to do here. One thing that I can do here is I can say, well, let me break this into two different sums. Okay. So right now there's one v here. I'm going to break this in. I'm going to say now pretend instead of one v, there were two v's. Okay. So I don't know exactly what to write yet, but I'm going to write this as a supremum over, let's call it v1. And this is t, the energy of v1 minus t rho 1 v plus supremum over v2. This is t v2 oops, 1 minus t minus 1 minus t rho 2 v2, which is, if you notice, this is exactly t f of rho 1 plus 1 minus t f of rho 2. This is the thing I want, right? The only thing now is I have to say, well, what happens? I did two different sums. I did two different maxima instead of one maxima. What does that mean? If I maximize over two things instead of one thing? Well, the maximum, when you don't force V1 and V2 to be the same, will be higher than if you force V1 to be the same. So this, if you like, this is the supremum over V1 equals V2, right? Which was fine, right? That was the truth. There was one V that had to fit in both of these pieces. Now I said, I relaxed the constraint. Relaxing the constraint makes this greater than or equal to 0. And so this makes it convex. Okay. So it's as simple as if you optimize, you know, a function of two variables and you say, let me optimize with respect to a constraint that x equals y, that's less than if you say, oh, and x optimize over x and y separately. That's what you did here. Right? So this is convex, and it's the same reason that this other thing is convex. So I only do it at the point that I've decided to break this term into a t plus t minus t. I have a rho 1 and a rho 2. In the first term here, there's no rho 1 and rho 2 at this stage. I mean, they're just v's. There's no rows. Oh, here? Oh, no. So this is the Legendre transform. So at the conclusion of everything, this psi gives me, so when I do this at the very end of this procedure, the psi gives me this density, right? The density only at the end, only at the supremum does it psi. This isn't a constrained search. This is the Legendre transform. So the constraint is relaxed. Exactly. Yeah. So this is not psi that gives rho. It's search over all psi. That's the handy thing about this is you're within the convex set by definition, right? Right. So this is where that little result came from. That little result on the meta GGAs came from this same argument, but with, yeah. So, I mean, you could argue that I don't care because the place where this happens, you require this as local effective mass, but it's technically true, right? It's, you know, whether or not you want to impose the constraint is up to your own pragmatism. Okay. So how am I doing on time? Oh, I'm okay. Okay, so that sort of is a, if you like, a digression. I challenge anyone who wants to. I've done the math. It's fun to go through these meta GGAs and take their second derivative and show, oh, yeah, that's not always positive. It's a fairly easy, but these meta GGAs, unfortunately, well, in fact, if you go down a couple of slides, no, up one, two, one more, and no, this one. Okay, so this is the form of a meta GGA. And this is meta GGA made very simple. This is the absolute simplest meta GGA. So this gives you an idea of the math that shows up because everything else is worse than this, right? So this is the exchange for uniform electron gas. So it's negative. That means if you take the second derivative of this with respect to, well, it turns out alpha is the thing you're going to need, but we'll understand that in a second. Then this needs to be negative so that times a negative, it's a positive, right? Because it should be positive. So next slide. So this is the reduced density gradient. That's fine. Next. And then this is the enhancement factor as a function of alpha and S. And then this is the thing as a function of alpha. And then this is alpha, right? And alpha, if you d alpha dt is just 1 over Thomas Fermi. So that's positive. It's just linear. So it means the second derivative with respect to alpha of this thing has to be negative. And you can just sort of look at it and go, well, it would be sort of surprising if that were true, right? And it's not true. I mean, we saw the plot, right? So in practice, this is the, you know, this sort of argument you have to go through if you want to do it. But I mean, taking the second derivative of this is it's okay. It's okay. You can do it. But it's a full page, right? Okay, back to the blank. Yeah, here, perfect. Thank you. Okay, so that was sort of a little bit of a digression onto, you know, back into kinetic energy functionals. And the other thing we were talking about last time was this one electron density matrices. We did the interreplicability constraints for them. And I was just beginning to tease the fact that there's a new approach on them based on optimal transport, right? I want to just go back into this. And well, number one, I did it hurriedly last time. So we're going to do it a little bit slower. And we're going to talk about how this expressed, how this is actually useful. Okay. But sure, while we're at it, why don't we play our little game because we're getting good at it now. And we're going to do in-representability constraints on the one matrix function. Okay. So it's going to be the same as what we've seen, but let's just do it just so we understand what's going on, right? So the in-representability constraints, the one matrix functional is the electron-electron repulsion. You have to write in terms of the density matrix, right? And the functional that we have for this is the supremum over one body potentials of psi with a minimum over psi minus trace of H gamma. Now, I should be a little bit more precise here. It would be much better to write this as a minimum over the density matrices because we don't really know the irrepresentability constraints otherwise. I can just watch out because I'm going to erase and then I'll rewrite with a little bit better form. That's more intuitive because I think most of us, certainly I am more comfortable with that. But it's equivalent to saying the minimum over gamma n of the trace of okay. So that's the ensemble constraint search. So you have to multiply the Hamiltonian by the density matrix and take its trace. That's the way you get the energy. Right. And we wrote these out. Like last time, you remember, we did this like sum over the ensemble. We had the weights and the wave functions. We optimized the weights and the wave functions instead of optimizing the density matrix. It's the same strategy. Right? So this is the exact functional, but of course, we're only dealing with approximate functionals. And the approximate functional is, you know, there's some in-electron system that such that when I leave out just one electron and I trace over all the others, I get back to one electron density matrix. I have to multiply by a normalization factor. That's just convention. And that it gets the right electron-electron repulsion, right? And again, the set of density matrices that satisfy this constraint is going to be convex. And so I have a convex set of VE and gamma, right? This is the VE values and gamma values that can come from some gamma n. And once again, if I have some bad guy out here that's not irrepresentable, then I know that it must be that there's some hyperplane, and the hyperplanes all are ground states of this, that this is too low for, right? So what does that mean? That means that there is K E tilde plus trace of, let's call it H tilde gamma tilde is less than the minimum over all the density matrices of the energy expression that corresponds to this. And the energy expression that corresponds to this is going to be trace some I equals 1 to n H tilde Ri plus K VE tilde times gamma n. Okay. Right. So this is my irrepresentability constraint. Is it especially useful? Well, not exceptionally so. It's a little bit more useful to write it as, now let's play the game again. VE of tilde, I'm going to divide everything through by K because I'm allowed to do that, right? It's less than the minimum over gamma n of the trace of right? So there'll be some H tilde such that this is true, right? Now, H tilde divided by K is just a scaling, right? So if I want to say this, this is just saying that there will be some case and now I'm just going to write this more explicitly. Some I equals 1 and of H tilde tilde of Ri. Which is just a different way of saying if I pull this over to the other side, there's some system exists, some system, I'm not saying what it is, where the energy with your approximate functional is below the true ground state energy. So that's the universal constraint always, is that somehow there exists some system, I don't know what it is, but there exists a system where if these two are not irrepresentable or not jointly irrepresentable, you'll get to below the true ground state energy, right? Okay. So same game as before. We could, once again, you could also say the same argument as before, as we just did. This VE of gamma is convex, right? From exactly the same argument, because it looks exactly like the same functional. So VE of gamma is convex. There's an irrepresentability constraint on your approximate functionals. It's not a very useful one, but it exists, right? Okay, so before I go further, do people questions about that? Okay. Either everyone is sleepy or I'm exceptionally clear today. We'll see. Okay. So I wanted to talk a little bit about this optimal transport strategy. And I think it's a nice way of thinking about this irrepresentability problem. So let's go back again, and we're going to just sort of review, because I think it was new to basically everyone, this idea of the classical optimal transport. I'm going to play a game just to try to draw a link into something that some of you may have seen, which is we're going to talk about the way that classical optimal transport shows up in density functional theory. Okay? So it turns out that the classical optimal transport is relevant to density functional theory, albeit only in a very special limit. Okay. So you think about the exact best way to do this. Okay, so let's remember again what the idea of classical optimal transport was, is that there was some cost. We said it had two variables, and we minimize the cost of these two variables subject to the constraint that okay. And we said that this was as if you had some distribution of resources and some distribution of customers. There's some cost associated with taking the resources from where they are to the customers, and you would try to minimize it. So the classic case is that you use the absolute value of x minus y. That's called the Wasserstein distance. Right? Something like the Earth mover distance, right? So let me tease you a reason that this is interesting to you as chemists, okay? So okay. We're gonna write frequency, and we're gonna say, let's say that this is the intensity of some spectrum, and let's say that this is the intensity of some spectrum with with DFT, and maybe this is the intensity of the spectrum. Well, let's choose something better than DFT. Let's say it's CCSD. Okay. So this spectrum might look like this. This spectrum might look like this. And this spectrum might look like this. Okay. So these are my spectra, right? Now, with your eye, right, you say CCSD is better than DFT. Everyone agree, right? I mean, we aren't talking about the cost. The cost was me drawing them on the figure. It's, you know, okay. So the normal way we would measure this, right, is we would say, oh, why don't we take the integral of I, let's call this I0, omega, minus I of, say, DFT of omega, and we'll raise it to some power P, d omega, and then we'll have to take the 1 over Pth power, right? Okay, so let's think about this, though. So this difference looks like this, right? If I do the same thing now, so this was for DFT. If I do the same thing for a couple cluster, the difference looks like this, right? Is there a question? Okay, no. Right, I probably, let me make it a little bit better artwork than I've done so far. But these two functions, when I take their absolute value, are exactly the same, right? Or their integral is exactly the same, right? They're both equal to the integral of this plus the integral of this, right? It didn't have anything to do with the fact that, oh, there was some, you know, sliding it further over didn't matter. As long as there was no overlap between this curve and this curve, the integrals are all the same, right? But from the optimal transport, the amount that it takes to move this distribution 1 unit versus 3 units is much less, right? And so optimal transport is a better way of measuring the quality of a spectrum, for example, right? So this is why, you know, maybe this was the first example of optimal transport in chemistry, right? It's just measuring the error in a spectrum. It's a much better way than the normal way you would do it, right? So it's robust to translation, basically, is what it boils down to. Okay, so remember this. Now I'm going to try to give you a concept where this shows up in DFT, okay? And actually, it also has something to do with kinetic energy. Also, that'll be a fun little link. Okay, so you may remember in DFT. So we're going to go back. The exact functional. I'm now going to write this in the Levy constraint search way of writing it. Okay. So we're going to do a minimum. I'll use it over wave functions that give densities. And we'll have wave function and we call this F lambda. So this is the adiabatic connection, right? Is if lambda wasn't there, then this would be a non-interacting system, and this would be constant kinetic energy. When lambda is 1, then this is the functional we know and love. People integrate it from 0 to 1 to get the exchange correlation hole. It's the standard tricks, okay? Now, I'm going to play a game which is say, well, lambda equals 0 was easy. What about lambda goes to infinity? Okay. Now, lambda goes to infinity is unpleasant because this thing goes to infinity, right? So I'm going to play a game. And so I'm going to instead, I'm going to do f lambda of rho divided by lambda. Okay. So I did almost nothing. I divided by lambda, but now it's obvious that, you know, when lambda is much, much, much greater than 1, that the kinetic energy is negligible, right? So this quantity gets killed off when lambda gets big. Now, we've understood that in DFT for a long time. We talk about, you know, lambda going to infinity. It's the strongly correlated limit. It means the potential is much more important than the kinetic energy. But if the potential is really, really important, then you can ignore the kinetic energy, right? And that's what this is, just a formal way of saying. In this limit, we don't need to worry about kinetic energy. It's 0, right? Right? You can build a Taylor series in 1 over lambda around the limit for the kinetic energy. It ends up looking like classical. So it turns out if the kinetic energy goes away, right, then I have a wonderful little result that I don't need to worry about anything kinetic energy. This is a classical problem. Okay. So now I want to just rephrase this as a classical problem. Okay. So I'm going to take this. So we're going to call this maybe f tilde infinity of rho. So I'm just going to take the limit as lambda goes to infinity. The kinetic energy is now gone. I have minimum over wave functions that give the density of psi. And now I'm going to write this I equals 1. And well, I'll be a little bit sloppy, not too sloppy, a little bit. Okay. So I did nothing. I just wrote out this and I said, oh, I take the limit as lambda goes to infinity. So that term dies off. And then I said, well, I'm going to see what this thing looks like. It's going to be a number, right? I don't know what the number is going to be, but it's a number, whatever it is, right? Now this is psi star times psi. There's no non-local operator, right? So I can rewrite this as a minimum over okay. So, right, the in-electron distribution function is just psi squared, right? That's the probability of seeing in electrons at different pieces in space, right? And the only constraint on it is that it's greater than or equal to 0, and its square root is 1. Right? That's the only constraint. Now you could say, oh, but I don't believe that. I don't believe you can put multiple electrons at the same place, right? Because of the Pauli exclusion, there should be some extra constraint there. It turns out that that's a constraint of measure 0, so it doesn't matter, right? So you can impose it, and it ends up being important at higher orders of 1 over lambda, right? But at the limit, doesn't matter anymore, right? A different way of saying it is because the electrons are repelling each other, right? There's 0 probability of them being on top of each other anyway. It's never going to be your solution. So, okay, but now I'm going, yep. What? So that's what I said. So at the classical limit, the need for antisymmetry vanishes. So the only thing antisymmetry means, right, is that you never have two electrons with the same spin at the same point in space, right? That's all antisymmetry means. So it just means, now I gotten rid of spin here, so I'm doing it spin free. So then this would mean you never have three electrons at the same point in space. You have an up and a down, and then another up would be forbidden. So you never have row of one, R1, 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 right? But the minimum of this, because this is a repulsive potential, never has that true. It never ever has two electrons even at the same point in space. So the Pauli principle is satisfied exactly, and it doesn't matter whether you have electrons or bosons or classical particles, it's satisfied because of this. Because this would be infinity, right? I don't know what the number is here, but it's not infinite, right? So it's a real, it's the one reason, oh, okay. So I've had a lot, this for the few of you who don't know, this is what Paulo Gori-Georgi has been doing a lot of for the strongly correlated limit, is mapping onto optimal transport in this way, right? And I remember when she first started working on this, and I was talking to her, and I said, the thing I don't like about this is I believe the fact that these are fermions is important, right? And it turns out that you have to go very far in the perturbation expansion around infinity before it even matters that you have fermions. Like, it doesn't show up at any of the leading orders, right? So it's a fine constraint, it's a good correlation constraint, but it knows nothing about fermions and bosons. And obviously the function was very different, right? Okay, so now I'm going to just rewrite this. This is minimum of an integral. This is some cost function, it's positive. Here's a distribution function, and the only constraints that I have are that the integral of rho of n of R1 up to Rn, that's a right? So integral, if I leave out the first electron, I get the electron density as a function of the first electron. If I leave out the second electron in the integral, I get the electron density in terms of the second electron. All of them have to be the same, right? Because they're identical. But this is a special case of this optimal transport problem, where the two distributions that come out are the same, right? So this is the way it shows up in DFT. Okay. So now we're going to go back and we're going to do this for density matrix functionals. And I'm going to say, well, VE gamma was the minimum of the trace of VE times some n electron gamma subject to the constraint that right? So I can leave out any of them. I can have an electron density matrix. I can leave out the first coordinate. I get the first order density matrix. I can leave out the second. I get the first order density matrix. Doesn't matter which of them I do. But this now is what they call quantum optimal transport. Because the only thing I did is I replaced my integrals with this sort of trace, right? I no longer had the ability to get rid of the kinetic energy, if you like, right? So I'm stuck now, but this ends up being well, it's a new trick to play with density functionals. It's the functional. This is nothing but the Valone functional, but it's just to say that, you know, with the benefit of more modern mathematics, this isn't just the same thing. We have a mathematical framework for this. Okay. That. Well, this is valid for ensemble, because
Time for one or two questions. If we have. No, we don't have. Don't be shy. Don't be shy. No? Okay, so thank you, Professor Ayers. So looking forward to seeing in the next session on Thursday. See you soon. Bye.